In a previous lecture, I showed you, let's say, a few of the general approaches to preconditioned coupled problems. So problems that have more than one variable and typically more than one kind of variable. Let's say Stokes has the velocity and the pressure, or in thermoelasticity you have the temperature and the displacement, and so on and so forth. So essentially what I showed you are all of the approaches that don't work. Things that we have tried in the 80s, 90s, and early 2000s, and that ultimately have not really been very successful. So what I would like to show you in this lecture is essentially our current thinking about these sort of things. So what are the things that we have learned do work and that are being used in large applications, in large computations with millions, hundreds of millions, billions of unknowns, for example. So essentially what I showed you in the last lecture is that this idea of using point solvers does not really lead anywhere, that we cannot think about solving a local problem at every node and then updating the variables that correspond to this node and then moving on to the next node. That turns out to be an approach that is not very successful, primarily because it suffers from the same lack of efficiency as, for example, SSOR or Jacobi, namely that you propagate information only from one node to the next in every iteration, and that's just not enough. Rather, what we need to do is we need to come up with ways how to not look at the problem, let's say, on a node-by-node basis, but that we look at this on a global basis. And what that means in our context is that we will have to look at the blocks of this matrix, and that if we can utilize the blocks of this matrix in a clever way, then we will come up with very efficient preconditioners. So what I would like to do is I would like to introduce you to the concept of block preconditioners. Back in the, I would say, late 90s and early 2000s, they were often called physics-based preconditioners. And I'm going to walk you through a little bit the history of how we got there, why we started out talking about them in terms of physics-based, and then why we now call them block preconditioners. So this is an ongoing research area. As I say, it started in the 1990s. I think we have roughly figured out how to do it, but there are still a lot of papers being written today. Today is in 2013, trying to figure out ways to make this work. So let me talk you through the, let's say, historical development, because that gives you a fairly good idea of, let's say, how we think about these sort of problems. And I would like to look at a particular model problem, that, namely thermoelasticity. So thermoelasticity, you can think of it in the following ways. So let's say I have a heat equation that describes how heat diffuses in a body. And there's a source term here, Q. So that would be, for example, the internal heating, or you could also think, let's say, if the source term only acts on a boundary, that would be the temperature that we prescribe on the boundary. Coupled with this heat equation, I have a second equation that describes the displacement of the body. So that is described by an equation that we call the elasticity equation. The solution variable of this equation is the displacement at every point, so the x, y, and z displacement of every atom in our body. And it's an elliptic operator. It's maybe a little bit hard to see here, but it is certainly symmetric and leads to a very nice and positive definite matrix. On the right-hand side of this, let me assume, for example, that I have no internal forces and maybe also no external forces. But the boundary conditions don't play that much of a role here. On the right-hand side of this equation, I have a term that consists of the gradient of the temperature. So what that means is that the temperature or temperature gradients induce a deformation of the body, right? If I heat it in some part, it's going to expand. If I cool it in some other part, it's going to shrink. So the temperature plays a role into the second equation, and similarly, the displacement is going to play a role in the temperature equation. Namely, if you can easily imagine, you may have tried this at home, that if you take a piece of metal, for example, and you keep bending it back and forth, it becomes hotter and hotter. So if you maybe you tried this maybe with a wire or so, if you keep bending it in a place where you have all of the deflection, or let's say actually it's not the deflection, it is the gradient of the deflection that plays a role, and in particular the time derivative of it, you produce heat. And so in these equations, what you have on the right-hand side of the temperature equation, you have a term that consists of epsilon of u dot. So u dot is the velocity, epsilon is the symmetric gradient of it, and we call this the strain, times c, that's the stress-strain tensor, so that is the strain times the stress, that is the heating rate. So in this sort of coupled problem, if I bring all of the unknowns that I have, the t and the u, over to the left-hand side, and I apply one time step, let's say with the implicit Euler method to it, then I come out with a linear system that looks like this. So I have m plus there's the mass matrix on the temperature times the time step times the Laplace matrix on the temperature. That comes out of this term here. I have some term that in reality is nonlinear because I have the square of the velocity here, but let's say I have linearized that somehow. So I have something that depends on the temperature, something that depends on the displacement that shows up in the temperature equation. And then I have the displacement, the elasticity equation down here, where c is the elastic operator, minus b comes out of this term here. So what you often have in these sort of problems is that the off-diagonal blocks are relatively small. So that should not read that c and e are small, but what I really want to say is that b and e are small. So these off-diagonal blocks here are relatively small in some sense. Certainly in this particular problem here, E is small. What you find often is that, let's say you have a slow diffusion process for the temperature. The temperature changes over, let's say, tens of seconds or minutes, for example. And then at any given time, you will see that, or you will have noticed that there is no time derivative here. At any given time, the temperature field that we have leads to a certain deformation. Now, the deformation does change with time because the t changes, but it changes very slowly, and as a consequence, the velocity of change is relatively slow. So this term here is going to be small, and certainly much smaller than this one. Now in this matrix form, that means that E is typically much smaller than B. But even then, B is typically still smaller than C. The internal forces that come, for example, from the boundary conditions on the displacement are going to be typically larger than what you have from the heating. So given this sort of consideration, if I say that B and E are small, then I may be able to approximate this matrix by something where I just drop these off-diagonal terms. And that would suggest that maybe a good preconditioner would be that I drop these off-diagonal terms, and I just take this matrix like it is and take it to the -1. And that means that I would have to take the inverse of this block and the inverse of this block. So let me consider what that actually means when I take this as a preconditioner. So if I consider this as a preconditioner, I told you that when we apply a preconditioner, let's say I give you a vector xt and xu for the temperature and for the displacement, then in every CG iteration or every GMRS iteration, for example, applied to the full coupled problem, I would have to multiply with p to the -1. And if I multiply it with p to the -1, I get the preconditioned vector xt pre and xu pre. So this is given. This is what I want. If I choose p to the -1 like this over here, then of course computing xt pre and xu pre out of xt and xu is exactly equivalent to, well, let me take this matrix over here, multiply from the left and the right with, from the left on both sides of this equation with p, and that means that I have to solve a linear system of this kind here. So I need to solve for xt pre with m plus delta ta, and for xu pre with c, right, with the elasticity operator. So in other words, applying this particular preconditioner that I have up here essentially means that I have to do one time step for the temperature equation and one time step for the elasticity equation, where on the right-hand side I have xt and xu. So we call this a physics-based preconditioner because I have to do one time step for the temperature physics and one time step for the elasticity physics, right? And I have completely decoupled this. So I do one step for one physics, one step for the other physics. And you can easily see how I can generalize this if I had more physics than just these two. So now, why would that be a useful approach? It is useful because typically I have fairly good solvers for each physics individually. For example, what does it mean to solve c xu pre equals xu? Well, it means that I have to solve an elasticity equation. And the elasticity equation is, well, it's a couple problem, but the matrix that comes out of it is symmetric and positive definite, and we know very good solvers for this, right? We, for example, would apply a multigrid method for them. The same thing is true for the temperature equation. So for the temperature equation, I have to solve m plus delta Ta times xt pre equals xt. Well, that means I have to solve for this matrix here. Well, M is a mass matrix, is symmetric and positive definite. A is symmetric and positive at least semi-definite, times the delta t. I know how to solve this sort of problem. Again, multigrid would be a good candidate, but I can also apply just CG, let's say with SSOR. So typically, for each one of these, what we call physics, I have very good solvers already because I have decomposed my coupled problem into individual uncoupled problems for which I have good preconditioners or good solvers. So this is a big step forward to recognize that I can solve these sort of problems by preconditioning not with something that is based on individual nodes, like in the Wanka smoother, for example, or the Wanka preconditioner, but if I look at this at a global level, that I don't want to look at every node at a coupled thermoelasticity problem, but that I want to look at a elasticity problem on a global level and a temperature problem at a global level. So you can think of this as a block Jacobi in some sense, because I have neglected all of the off-diagonal blocks, and I'm just going to consider the diagonals on these blocks here. I can, of course, do the exact same thing as I have done for SOR and SSOR, for example, or let's say Gauss-Seidel, where I'm, instead of throwing away all of the diagonal blocks, I only throw away those on one side. So let's say I throw away this minus e here, but I keep minus b. Okay, this is now a block triangular matrix for which I can relatively easily form the inverse. That's just a forward substitution. Or I could throw away minus b and keep minus e and take the inverse, and I get the inverse of this upper triangular block, which means I have to do something like a block backward substitution. So which one to choose, of course, depends on, well, I want to throw away the smaller block. So typically, in this particular case, I know that E is typically smaller than B, so I would go with this preconditioner here. But I can easily construct cases where, let's say, for whatever reason, the material does not depend, the displacement does not depend very strongly on the temperature, so minus B would be fairly small. But for whatever reason, the velocity of displacement is large, and so in that case, I would want to go with the preconditioner down here, where E is larger than minus B. So depending on which term is bigger, I want to throw away one or the other. In any case, I come up with a block triangular system. And if I do this, then I can ask again, well, what does it take to actually multiply with this preconditioner? Well, here, now let me multiply with p again. That means that one preconditioning step means I have to solve with this particular matrix here, where I now have this term E here. So I can do this in the first step. I solve C xu pre equals xu. That is just an elasticity solve. And then, since I know xu pre, I can bring this to the right-hand side, and the second step would involve m plus delta t a times xt pre minus e xu pre. I can bring this to the right-hand side, and so in the next step, in the next equation, I have to just solve this block here. Well, that's exactly the same kind of steps that I needed to do with the block Jacobi, that I solve an independent temperature and elasticity problem. So the effort here is exactly the same as before, except that I have taken a lot more of the coupling of my matrix into account. So this whole thing shows that I can construct preconditioners for coupled problems if I respect the block structure of these matrices. And that turns out to be a really useful, really practical, really efficient way of doing things. So these, what we call physics-based preconditioners, are very efficient. Typically, if, let's say, you had a problem that is not strongly coupled, then you should be able to solve this, let's say, in 5 or 7 GMRS steps, where in every step of the GMRS method you solve one temperature and one elasticity equation. So these are two global equations, but for both of these at least we know how to solve the equations efficiently. So the basic insights are that these preconditions are often really, really good. They are particularly good if the coupling is primarily one way. For example, if the temperature affects the displacement much more than the displacement affects the temperature. In that case, you should be able to get away with a very small number of outer iterations. Okay. In particular, these block preconditioners are often much, much better than point preconditioners, like the Wanka method. And they can certainly be generalized to problems with more than 2 physics. So if you want to add chemistry and this and that, you see how you play with this. You drop certain terms and you come out with something that is block triangular, for example, and then you can apply the same kind of methods where you solve for one physics at a time. So the big question then is, let's say now that I know how to do these physics-based preconditioners for problems where I have multiple, let's say, different physics, can I generalize this, or can I apply what I learned to equations like the Stokes equation? So the Stokes equation is down here. So I have the Laplace term, the gradient of the pressure, the divergence of u, and so the matrix that comes out looks like this. And so in this particular case, you are faced with a certain conundrum, namely that the variables that I have do not correspond to different physics, right? So the temperature and the displacement, they were different physics that happen to couple with each other. But here, the velocity and the pressure are certainly part of the same physics, namely of the flow problem. They belong together. And you can see this by the fact that there is no matrix here on the diagonal. I can also not say, well, I want to drop B or B transpose, for example, because then my triangular matrix becomes indefinite. Not just indefinite, it becomes not invertible, right? If I drop one of these terms, I end up with a matrix that's not invertible anymore. So I cannot immediately construct preconditioners out of this, but I can follow the same kind of concept as we had before, namely that I want to take into account the block structure of this matrix to construct a preconditioner. And so the answer to this question, whether I can use these insights from physics-based preconditioners for single physics coupled equations, the answer to this is yes. What we need to do when we want to do this is to understand something that we call the Schur complement. And so let me walk you through this real quick. So the Schur complement comes from the following realization. So if I start with the Stokes system, I can think of this, of course, as two equations, AU plus BP equals F and BTU equals 0. So these are these two equations here. Now let me multiply the first equation with a to the minus 1. So I get U plus a to the minus 1 BP equals a to the minus 1 F, and the second equation is what it is. then what I've done here is, of course, at least formally, I have singled out u. And so I can say u equals a to the minus 1f minus a to the minus 1bp, and I can stick this here into the second equation. So if I do this, I come out with an equation that looks like this. B to the minus bt, a to the minus 1b times p equals bt, a to the minus 1f. So here I have an equation that only involves the pressure, right? So I've just decoupled these two equations. And I can use the second equation to solve for the pressure. And when I have the pressure, I can stick it in here, and then I end up with an equation that is only for the velocity. So actually, if I have the pressure, I would stick it into this form here. B times the pressure, I would bring that to the right-hand side, and I would solve for u. So this sort of process, we call this a block elimination, because I have essentially done something like a Gauss elimination on this matrix here, except that I haven't looked at individual matrix entries, but individual blocks in this matrix. But if I do this, I come out with this matrix bt, a to the minus 1b. That's the matrix that I need to invert to solve for the pressure. And this is the matrix that we call the Schur complement. So in particular, it's the Schur complement with respect to this particular block here. So what can I do with this? So if you look at this, I ended up with two decoupled steps. I needed to solve this linear system SP equals something on the right-hand side, and if I have the pressure, I can solve for the velocity. The problem, of course, is that I don't really know S element by element, right? It contains a to the minus 1. If A is a sparse matrix, a to the minus 1 is typically still a dense matrix. So S is a dense matrix, and in particular, I mean, if I can solve a to the minus 1, then my problem is almost solved anyway. So I don't have a to the minus 1. But what I can do, of course, is that I do the same things as we discussed in step 20 and 22, namely that every time when I need to apply S in, let's say, a CG method for the pressure, so S is a symmetric and positive definite matrix in this case. Every time I need to apply S in the CG method, well, I would first apply B, then I would apply a to the minus 1, which means I need to solve a linear system with A, and then I apply B transpose. So I can work with this somehow. This is a matrix that maybe I don't know it element by element, but I can certainly apply this matrix to a vector, okay, like we did in step 20. So for now, this is more of a conceptual approach. So step 20 actually shows how you can make this work. In step 20, we actually solve a problem like this. Not the Stokes equation, but a mixed Laplace equation, but it has very similar properties. So what can I do with this now that I have an approach? Let me look at this in a different light again. So if I look at this problem, at this couple problem where I need to solve S times P equals something on the right-hand side, and then A times U equals something else. That actually corresponds to the following problem. So S times P equals something on the right-hand side, and then A times U plus B times P. Well, so this linear system here is entirely equivalent to the original Stokes system. So if I were to multiply this linear system here with the inverse of this matrix, I would get U and P as the inverse of AB0S to the minus 1 applied to this thing here. And I can form the inverse of this matrix here because it's triangular, it's block triangular. The inverse of this matrix looks like this, okay? And that suggests that, well, so what is the perfect preconditioner? The perfect preconditioner is always the inverse of the matrix, right? I have an equivalent problem here as I had to the original Stokes problem, so that suggests that maybe this one here would be a good preconditioner for the Stokes matrix. And that is indeed what a lot of people use. So it suggests that we take this matrix as the preconditioner for this thing here. And I can multiply this out. I can see what happens if I do this. So you will have noticed that on the right-hand side, I don't have F0 like I had over here, but I had something else. So this is not exactly the inverse of this matrix, but it certainly comes close. If I multiply it out, I find that the product of this matrix and our preconditioner has identity blocks on the diagonal and something over here. So if you do this, you can show that for this particular preconditioner, if you use this in the GMRES method, for example, you will converge in exactly 2 steps. You would converge in 1 step if the product had been just the identity matrix. It's not the case here. But you converge in exactly 2 steps, and that was shown in a paper by Sylvester and Wathen in 1994 that revolutionized the field of preconditioning the Stokes equation. So this is really one of the fundamental papers in this area. In practice, of course, this sort of preconditioner that I show you up here is theoretical because I do not have s to the minus 1. As a matter of fact, I don't have s. And I don't have a to the minus 1 either. But I can make something out of this. Namely, if I can't do this as I have written it here, maybe what I need to do is I need to approximate a to the minus 1, and I can approximate s to the minus 1. So these tildes mean approximate inverses. For example, I could do 1 multigrid step here, or 1 SSOR step, instead of applying the inverse of the matrix. The question is what to do with this s to the minus 1. And there's some theory that you can apply to this. So s corresponds to bt a to the minus 1b. Well, b is the gradient, bt is the divergence, a to the minus 1 is something like the inverse of the Laplacian. So if you write this down in terms of the operators, you have minus divergence minus Laplace to the minus 1 gradient. If you were to switch these two around, assume that they commute, you would find minus Laplace times minus Laplace to the minus 1. That would be the identity operator. And you could suggest that maybe the appropriate approximation for s to the minus 1 would be just the inverse of the mass matrix on a pressure space. So this is what people really do. They approximate this one here, for example, with 1 multigrid step. They approximate this one here with inverting the mass matrix. And that yields a very efficient preconditioner. So you can take a look at this in step 22 in the results section where we discuss this in more detail. That is really a good preconditioner. I don't want to go into too many details here. It turns out that this reasoning that I can exchange these two operators here is completely flawed. And I don't want to go into details why that is so. That there's theoretically, I cannot do this because this acts on the velocity space and this acts on the pressure space. So I can't commute them. It works anyway, and there are good reasons for this. Essentially, the point I wanted to make with this is that when we play with these blocks of a matrix, we can come up with very efficient preconditioners that we can construct by well, inverting diagonal blocks if we know them, dropping certain off-diagonal blocks that we know don't have that much of an effect. If we know how to invert diagonal blocks, for example, because they correspond to an individual physics, then we should do this. And so to bring this all together here, if you play with blocks, let's say with individual operators like the Laplace operator or the elasticity operator, typically you can come up with very efficient preconditioners that are much, much better than the point-based preconditioners that we have tried to use in the last lecture and let's say in the 1990s. So today, all of the big problems, the couple problems that we want to solve, including the Stokes equation, for example, we always use preconditioners that are based on the block structure of these matrices, and that is much, much more efficient than trying to do it locally, node by node, for example.